I'm Michael, and this is Ann, and we are here to talk about how we use kind of Spark Mllib models in our production training and serving environments. So just a quick introduction. We're from the Michelangelo team, which is Uber's machine learning platform that essentially supports end-to-end training, serving, evaluations of machine learning models in production at scale. So in this talk, we kind of want to walk through our journey with Spark as we evolve Michelangelo's architecture, and just share some of the experiences as well as learnings learned along the way. So we started just like many others. We have some kind of monolithic system that kind of handles training and serving. We know we want to do distributed data ingestion, model training, batch, and real-time serving. Essentially, Spark is a very comprehensive framework that essentially captures a lot of that, right? So we kind of started with Spark. We cloned it. We introduced some kind of custom Uber-specific Protobuf representation of our models. We kind of extended or customized our transformer class to have this kind of low overhead online serving method. And then for each of the model types that we supported in the beginning, essentially we just kind of hard-coded, model pipeline definitions. For example, for a logistic regression model, maybe we have, string indexer and then vector assembler and then the base estimator for the actual regression model. Right. So obviously this worked pretty well for a while until it didn't, and we'll kind of cover why that is. So before we kind of go too deeply into why we started with using Spark pipelines and Mllib, I think let's kind of recap of what exactly are Spark pipelines. And as many of you know, Spark pipelines essentially are composed of different multiple stages. Each stage being either a transformer or an estimator. A transformer will take in a data frame, do some transformation, outputs another data frame. An estimator essentially takes in a data frame, will require certain computation on specific columns within the data frame, and then outputs the transformer. So this usually encapsulates some kind of learning algorithms. It could be linear regression, or if you just want to do a certain computation to do your data transformation, like if you want to do say min-max normalization on a specific column, you need to compute the mean and max of specific columns, and then output the normalized features, right? So. And when you actually execute a pipeline, you're essentially going through stages by stages, calling dot and dot transform. And what you get is a fitted pipeline or a pipeline model. And at inference time, after training, essentially we'll go through exactly the same stages and then output the final transform data frame that we desire. And so what does it matter, right? Because at the very beginning we started thinking about what exactly is a model. And obviously in the beginning we thought a model will just be whatever that takes in a bunch of data sets to train on it and then produce some kind of raw predictions that we can use. But obviously it's a lot more than that, right? It's like there's a lot of stages usually before you have your raw training data sets all the way to something that's consumable by your learning algorithm, for example. And usually that requires multiple data transformation steps, feature extraction, and then feature engineering. After you fit it, a lot of times you have some kind of post-fitting or post-scoring transformation, like if you want to transform your label to some kind of space that can be consumed by your downstream services, or you want to add additional data like some metadata, or you say if you want to do probabilistic calibration on your raw predictions, for example. And at inference time, you want the exact same kind of steps to actually happen as well, right? Because you have your raw test predictions. If you don't go through exactly the same step, essentially you're introducing some kind of stew or some kind of inconsistency between your predictions, and that would be bad. And essentially what the Spark pipeline models provides us, essentially, it kind of captures this idea of some kind of consistency we require in different environments, and kind of provides some necessary abstractions for us to handle this. So what we were really saying is, one of the first benefits that we really want to go for, or one of the goals we want to go for, is we really want to have consistency between training and serving. Because imagine a typical workflow, some data scientist or research engineer is going through model iteration offline, right? And then you want to go through cross-validation, hyperparameter optimization, and then you have your final model. And then it's all great, you deploy it, but when you go through during serving, you generate basically something just slightly different from what you have training. Then you essentially produce basically a bad no-no for us, where you have predictions that's kind of unexpected. And a lot of times it's actually pretty hard to track these as well, right? Because, for example, if you encode whatever your raw prediction into some kind of like slightly less information space, where, for example, like, a binary classification, your raw prediction got mapped to either just a binary output. A lot of times like, it's actually very hard to detect whether there's actually any kind of differences between training as well as at serving time. But other than that, I think there was a lot of kind of complexity as we kind of evolve our architecture that we would like to kind of just kind of encapsulate, because as you all know, like I think within a machine learning workflow is very complex. So even within a data source, there's multiple data streams, data source, schema types, and then after we consume that, there's still like, there's real time, there's batch, and we need to ensure data integrity, compliance, and security. And after all that, like, we go through the typical kind of machine learning workflow where, as we just talked about, but there's still a lot of different kind of like libraries and frameworks kind of expected at different parts of the workflow. And there's also, sometimes different kind of, operational needs or business logic, right? Some things are kind of more relevant into one environment versus the other. Like, in offline model evaluation or training environments, you might need to do some kind of, say, cross-validation or some kind of train test splits. That is kind of is relevant in doing training, but not relevant in serving, right? So, or sometimes you need to do some kind of specific sampling, like say stratified sampling, to get your training or validation sets. But the thing is that we need to somehow capture all these. And actually, a lot of times, within a pipeline, even within individual stages of the pipeline, there could be specific business logic that we need to handle. For example, like we might want to have Spark distributed processing in one secure cluster and then transfer that output data into some other cluster that, say, have more GPU resources for, say, deep learning training, for example. So basically, how do we actually ensure that there's consistency between the different stages within the pipeline, and yet is easily decoupled, it can be decoupled and coupled back together, meaning that we need to find a standard way to kind of like easily serialize and deserialize these pipelines. And of course, there's also organizational needs where there's within the whole workflow, there's different kind of functional roles that kind of expects different frameworks and languages and the way they kind of deal with data, as well as like machine learning as well, right? For example, research scientists or data scientists might be requiring specific latest feature. Say in XGBoost 0.8, like we have checkpointing and monotonic constraints, whereas maybe the production is only still at 0.7, like which doesn't have that. So how do we kind of support that? And bridging a lot of these kind of frameworks kind of important, it becomes increasingly important for us, because as over the time, I think like there's more and more adoption within Uber, and then basically like we realize like any kind of custom support for these kind of requests are just not scalable, right? So given all those like complexities in mind, we kind of come up with two main goals. The first goal is, we like kind of our initial kind of monolithic system. We introduce a lot of, different kind of, say, online serving methods and our custom protobuf formats. I mean, there's pros and cons, which we'll talk about. But we like to kind of retain and, if not, improve the performance of, our batch as well as online serving. But I think the most important goal here is also to kind of maintain consistency, like we talk about, between online and offline, right? So first, I think, so essentially data frame essentially is built on top of Spark SQL engine, right? So it does a lot of different query optimization and planning and task scheduling and all that good stuff. So that's great for batch serving, and we need that, right? So, but the thing is that this also introduces a lot of like overhead, which could be up to the scale of like hundreds of milliseconds or even seconds, which is not acceptable for kind of low latency online serving environments like recommendation engine or even fraud detection, for example. So wherever we try to evolve to needs to still maintain, this online serving kind of environment, like performance where we have very low latency for P99, that's like less than 10 milliseconds, as well as high throughput, right? So, and at the very end, again, consistency. But on top of that, I think this, as we mentioned, become increasingly more important, which is, how do we have more flexibility and velocity in terms of development from both just the microinterval team as well as any kind of research scientist or data scientist that we work with, right? Because they kind of can control what they want to do in terms of each transformation stages, and as well as what the model they should look like. So we should kind of empower them to do a lot of that, right? So essentially what this means is that we need to have flexibility in terms of supporting different kind of model definitions, libraries, and framework, right? And not only that, like it's also environment, right? There's a lot of different kind of development environment within Uber, like our data science workbench, which essentially is some kind of Jupyter and notebook environment that they're all very accustomed to. They iterate, they experiment with the models on there. But there was a gap between experimentation as well as deployment. So how do we kind of bridge that gap? So we need to somehow find a way to kind of have different kind of Spark kind of pipelines, things that they were experimenting with, and find a way to easily translate to our online serving kind of framework and architecture. So that was another requirement. And last but not least is that, while our custom Protobuf format it worked, and then it was very quick. I mean, it's binary serialization, deserialization, so it was very quick. But we're kind of tied to kind of a lot of very custom stuff. So essentially, that kind of inhibits our kind of upgrade of different kind of, especially Spark. I think there was official supported version of Spark, and then it was very difficult to kind of upgrade and be aligned with that. So how do we also remedy that? So to kind of address all these, I think the first thing we did was to really come back to revisit kind of our concepts of model representation. What's the right way to kind of serialize and deserialize that? And then revisit kind of like how do we support online serving, and we'll kind of walk through a little bit of that.
Thanks, Michael. Yeah, so we, in our goal to retain the performance and consistency we got from our custom Protobuf, but to move to a world where we could be much more flexible about what models we could support and what we could interchange those models with in terms of other parts of Uber Stack, as well as being able to upgrade to more recent versions of Spark and bring that value to our customers, we looked at how to replace our custom Protobuf representation. And we looked at 4 main ways that we would think about encoding the models. And so these are the biggest hits of the things that are supported by Spark Mllib right now. Mllib, PMML, PFA, and of course the Spark pipeline representation itself. And for Mllib, it's great for doing online serving, but we felt like it had the same issues that we had with our custom Protobuf representation, which was, it's special and you can't interchange that format with other pieces of the stack that understand Spark serialization and deserialization, but not the special format used by Mllib. And for all 3 of Mllib, PMML, and PFA, there's some friction in supporting new Spark transformers. A new transformer comes into Spark, and these representations have to be updated to handle that new representation, so a little bit of velocity impact there. But the biggest thing we were concerned about was the risk of inconsistent model serving behavior. So you trained in Spark, you evaluated your model, you had a certain expectation. Now you store that model and load it in some representation that you hadn't evaluated, and you get a different behavior. And our manager said, you can have a bad model, but if the data scientist sees it bad at training and serving, that's fine. But if it's inconsistent, you're robbing them of the ability to make a judgment about that model and really misleading them. So that was the biggest concern we had. So we really wanted to use the Spark pipeline model representation itself to avoid these shortcomings. We thought it also provided a simple interface for writing estimators and transformers that our customers could use for those of our customers that wanted to write their own estimators and transformers. But it has several well-known shortcomings, which Pentreath did a good job of describing in his Spark Summit talk last year. Those shortcomings are the pipeline model load is too slow for online serving, and the pipeline and the predictions that interfaces that Spark Mllib provides are too slow for online serving. So, we care a lot about online serving. It's the most important part of Michelangelo, and so we really needed to, tackle these challenges if it had a chance of being our standard representation. So what does the Spark pipeline representation look like? Just quickly, it is, a structure, a file system structure of directories. There's a directory for each stage in the pipeline. The directory contains metadata description of that transformer stage, and it also optionally contains a data file or files that describe auxiliary data needed for that transformer if such thing is needed. For example, a batch string indexer would need an auxiliary file to map the strings to their representation. In the index, it's read and written by simple ML-readable, ML-writable interfaces in Spark Mllib. So basically, we took that representation and stored it in a zip file, and we compared the loading of that representation to the loading from our custom Protobuf representation of the models for 6 models that our customers really cared about. These are 6 different kinds of models that were running in production at Uber. And what we found is that the load time indeed was quite low. I mean, slow with the Spark representation. Out of the box, it was anywhere from 8 to 44 times the speed at which we could load our Protobuf representation. And these were for roughly comparable size files because the zipped files for the Spark pipeline were roughly comparable. So you could say, hey, who cares? You only load the model when you first start up the service. So, hey, it's slow, who cares? But the problem here was that it was so much slower that it really impacted our ability to do resourcing quickly. So for example, if the online serving infrastructure became too busy and we needed to spin up more instances of online serving and they needed to load hundreds of models, 8 to 44 times slower to load those models really did start to feel like we weren't able to respond with additional resources more quickly. And secondly, when a user deploys a new model, he or she expects it to show up quickly. There's a health monitoring on that. And the health monitoring faced challenges with this much impact on the speed at which we could load the models. So we looked for why are these model loads operations so slow? And there were 3 pieces of very large low-hanging fruit. The first piece of fruit had to do with the time it takes to load the metadata for each of the transformers. That metadata is a simple string file. Basically, it's a 1-line file. And Spark was reading it by forming an RDD of strings, and that was really quite slow. And so what we did is, when there's a local SparkContext like there is for loading online serving models, we just simply read that with basic Java I/O. And this was a tremendous speed up across the board on all of the metadata loading of model transformers. The second piece of low-hanging fruit had to do with those data files that we mentioned. Basically, the data files are keeping that extra data around for certain transformers that need that extra data, like including the Spark index, the string indexer, for example. And Spark Mllib was reading those with a distributed read select, and that was really quite slow as well. And we replaced that with a direct parquet read and get record, and that sped the load of these particular transformers up quite a bit. And the third piece of fruit was kind of related to the second piece of fruit, but was specific to the tree ensemble models, which are very popular at Uber. So these tree ensemble models have multiple data files that are coding different parts of the node and metadata weights for the tree nodes. And not only was there a read select, as in the case with data, but then there was a sort and a collect, and this was very slow. And it's, even for large trees, this is not a lot of data, actually. So we, again, replaced this with a direct parquet read and get record and saw a great big speed up. And what was interesting here is we saw a lot of speed up just by making these changes on the load side, but we still were left with the problem that on the store side, these model files, these additional data files, were often written as very small, a group of very small files. So there was no coalesce on the save file. So we added a coalesce on the save side to reduce the number of just files you had to open and process. And we can certainly, in our loads, process a save that's been done outside of Michelangelo that doesn't have that optimization. It's just a little slower. But if you are saving the model file with Michelangelo, you get a speed up there as well. So after making these 3 changes, you can see the last column here is the latency of Spark pipeline load versus the latency of our custom Protobuf. Still not faster. It's really hard to beat a binary representation that's custom. But it's 2 to 3 times slower, which we thought was well within the target we wanted to have for, it was a good price to pay for the flexibility that we were getting from using the pipeline model representation. So we're okay with this, and our customers are okay with this. And we rolled this out in production. It's been in production for about 6 months. And not only is it working well for the models we could already support with the custom Protobuf, but it's working well for other models that this enables. There was one other slight additional challenge I just wanted to mention because I don't want other people to run into this if you do go down the same path that we went down, which was we do crank up a local SparkContext for online serving, and we're using that. If it's a transformer that hasn't been tuned by us, we can still load it in the normal Spark Mllib code that hasn't been optimized. But the challenge was that every 30 minutes, our online serving latency would shoot up. And come to find out, that was the context cleaner running every 30 minutes to clean up the Spark, to do the special Spark garbage collection. So we actually, the way we solved this is just to only run the SparkContext when we're loading models. So we just stop it when we're not loading models, and that solved that. I'm sure there's other ways to solve it, but just wanted to mention that because was a little surprised we didn't think about when we were first rolling this out. But we discovered when we started testing at scale. So that's solving the challenge of the model load being too slow for online serving. So now, Spark pipeline model load for us meets our goals for online serving. But the second challenge was the idea that the normal Spark serving APIs are too slow for online serving because they involve a data frame and so on. So what we did was, we had some ad hoc, APIs that we had added, but we just decided to kind of formalize it under a trait called the online transformer trait. And that trait has two entry points. One is for score instance, where you give a map of features and you get back one prediction, and the other one is for a batch version of that same thing for a small list of items that you want predicted. And these traits are added to the transformers for which we wanted to support online serving in Spark. And this works well and gives kind of a framework for thinking about this. And this leverages low-level predict methods that are already in Spark wherever they're available. And of course, we can inject these methods into an existing model that was trained outside of Michelangelo. So you've trained a Spark pipeline. If that pipeline consists only of transformers that we support for online serving, then at load time, we sort of, in some sense, inject these and you can serve it online. So this allows people to train outside of Michelangelo, but still have Michelangelo do their online serving. So after all this, we feel like we do have this new world of Michelangelo that's more flexible, but retained the performance and consistency we wanted based on these two big, they're big to us, but they're small changes in the Spark code. And so I will turn it back over to Michael to talk about some use cases that having this more flexible model representation in Michelangelo has enabled.
Thank you, Anne. So again, just to recap, I think now we're at a stage where most of our pipelines are in some kind of pipeline model representation. We previously talked about that we need to kind of handle the different kind of business logic and operators in between different pipelines, and now we have an easy way to kind of do SerDes. Another thing to note is that for the online kind of serving part, where we usually in the transformer.transform, I think the interface expects some kind of data frame, which causes a lot of kind of the reduction of performance that we're talking about for a single row performance, right? So whereas in online serving, where we introduce the online transformer trait, the score instances essentially take in a map of kind of features so that we can bypass this kind of coupling with data frame kind of interface in some sense. So now that we have this brave new world, I think we have started seeing a lot of different kind of better adoptions, and then we're able to actually kind of allow different kind of parts within Uber, data scientists, research scientists to actually come in and contribute code that actually it will be very hard to scale if for us to actually support all of that ad hoc, right? So and let's kind of take a look at some of the things that we previously mentioned and see how and provide some examples of how we're doing there. So for the first one, I think we wanted some kind of very flexible pipeline model definition, right? So that data scientists, there might be different kind of frameworks or systems or language for different kind of estimators and transformers, and we need to be able to support that. There could be different kind of model types. For example, traditionally we supported almost everything in Spark, but there's new interest and need for, say, XGBoost models or TensorFlow models, how do we make sure that that's kind of coupled with our Spark pipeline as well, right? Because a lot of the, say, data transformation or processing, feature engineering still kind of relies on kind of our Spark processing. So how do we kind of couple that together? So one example is, this is from something we published last year, where we're trying to kind of leverage Spark pipeline to do feature engineering processing, but still being able to kind of train and serve a TensorFlow model, right? While kind of leveraging the existing serving infrastructure that we have built over time and has been very stable, right? So just quickly walk through it. So the flow basically is like this. This is kind of a V0 version from last year. I think we're making a lot of improvements to this, but the initial flow was basically like this, right? So we have some kind of training data in some kind of cluster, and we do different kind of transformation, fitted, non-fitted transformations. We got some kind of intermediate data record, like say TF record, and then we have to use some kind of operator to transfer it to some kind of other cluster that has GPU resource that we can use. And then we'll kick off some kind of distributed training job using, say, Horovod. And after that, we'll generate some kind of trained TensorFlow model. It could be saved as some kind of saved model bundle kind of format. And after that, will be deserialized back into our custom TF transformer that we implement. So in this case, we'll have to both implement a transform and score instance method so that the custom transformer knows how to actually handle what do we do in batch scoring and then versus online serving. And after that, we kind of have a separate operator that kind of combine the two pipeline models into a single pipeline, put it into model store, and actually deploy it to both online and offline environments, which essentially, like we talked about, will go through the respective stages in both the first pipeline to do transformation on the data, and then actually invoke the TF transformer to actually do either batch or online serving. And after that, obviously, we have post-scoring transformations, but that's another story. So, and what this does essentially is, now data scientists can come in, they can just implement a custom transformers, and then they can, use different kind of model types, that's kind of compatible. And then essentially they just have to implement different kind of score instance method or transform methods. Essentially they have the control over what they would actually like to use and what's the performance that they can dictate that essentially. And obviously we have different kind of checks to make sure this is compatible with kind of the performance that we're expecting. Another use case that we see a lot is basically we have different kind of environments within Uber. One of the more popular ones is this Jupyter Notebook environments called DSW, which was I think we gave a talk at Spark Summit about that as well last year. Essentially, a lot of data scientists would like to kind of do different kind of experimentation on the notebook environments, and then they will do try out different kind of transformers, indexers already provided in Spark, but they also want to add different kind of custom ones. And after that, there's different options, right? One is, whether if they can just directly fit the model within the notebook environment, they need to find a way to kind of easily kind of deploy that or upload that into Michelangelo and then still be able to serve that through the infrastructure that we provide. But the other option is that, let's say they were playing around with data sets and then they have a couple of transformers they require, but the thing is that maybe the data set they're working with is large. It's too large to be handled by, say, the DSW environments, and say requires some kind of custom components within Michelangelo to do different kind of distributed training, then we need to also find a way to kind of upload those pipeline definitions into a way that we can be consumed by our workflow framework that then we can kick off different kind of distributed training that we have optimized, right? So now they have essentially, because we moved to a more standard serialization, deserialization format of kind of our pipeline models, we kind of enable that, right? Because our workflow can kind of easily expect and read and write different kind of pipeline models. So, so basically, this is kind of the flow that we kind of talk about where, we go through all the process into a notebook environment. We have either a train model, we can deploy that directly, or, we have some kind of model pipeline definitions that we can upload that can be consumed by Michelangelo's workflow system and, actually carry out the actual distributed training or evaluations, for example, and then deploy just like a regular model that we have in the past while maintaining, the latency and performance requirements that we have. So, yeah, so those are kind of two examples of, to illustrate kind of the the things that we were not easily able to support, where in the past would have been quite a hassle, right? For like, in V1, for example, even if you just want to add an if statement to, say you want to add calibration to our pipeline model, we essentially have to append additional transformer into our pipeline, where now I think that can be easily handled. And some of the key learnings that we have, right, in terms of evolving is we thought, we realized that model pipeline representation is useful and it's actually been true. It's actually very powerful. It kind of encapsulates a lot of kind of the complexities that we have within a machine learning workflow, right? And it forces kind of, the right consistency between the different environments that we require, and then and provides the kind of flexibility that our users kind of require and demand. And just in summary, I think like Anne said, this has been going in production. It's been working out well for the past 6 months, and it will continue to kind of support different kind of more models, more frameworks, and more libraries. But at the same time, we're also trying to open source some of our changes, and based on the low latency as well as the online transformer trade that Anne just talked about. And we'll love to get any feedback there. And that's it. Great thanks to the entire Michelangelo team and questions.
If anybody does have any questions, you can come up to the mic.
Hi, I wanted to ask, do you guys use SparkML now over Mllib? And why did you decide to use Mllib?
We can answer it.
Yeah, we use SparkMLib. I'm not sure.
Yeah, we do use SparkML now. I think in the very beginning, back then when we used it in 1.6, I think we basically readily just used Mllib as a starting off point, and then we gradually evolved to Mllib. SparkML. Yeah.
Hi. You mentioned that with things like Mllib, you need to always worry about supporting new transformers. But isn't that the case with the online transformer trait as well, that where new Spark transformers are added, you need to implement that trait for those as well?
Yeah, that's a fair observation. I think what we found though is it's pretty easy. It's way easier because we've got experience in both areas. It's way easier to implement the essentially a score instance than it is to implement a new way of storing a new transformer in Protobuf. So A, it's an easier thing to do, and B, for a lot of the transformers, there is already a low-level predict that we can pretty easily call. For some of them, it's not. So basically, all the model transformers typically have a low-level predict that they make available. For the feature transformers, you usually have to write the score instance, but it's not a hard piece of code to write. So I agree with you that it's not zero work, but at least you're kind of doing that work in a pretty organized way. Yeah, good, fair point.
Hi. Are you guys still using RDDs, or have you moved from RDDs to Spark data frames?
Sorry.
So are we using RDDs or data frames?
Oh, we're using
data frames, yeah.
So I have a question about the performance improvement. After you customize SparkML library, for example, what I remember that if I use SparkML library for scoring, even for linear logistic regression, in fact, it takes more than 100 milliseconds because there are no overhead. After and in your case, what's the final latency? Is it 10 milliseconds or 20 milliseconds?
Are you talking about for scoring?
Yeah, for scoring.
Yeah, we have an SLA of less than 10 milliseconds for online model scoring. So we're able to meet that target with our thin API.
So in fact, we just did a third interesting testing. If we use Mllib, in fact, the latency is about 7 microseconds.
Okay.
This is more than 10,000 times improvement. And in fact, if you and this is different, and we implement our own logistic regression, and the raw code logic also take only 5 or 6 microseconds. So I guess in fact, if very possible, I don't know whether other people use Mllib. In fact, seems that Mllib is promising, but use since that the transformer, the customer transformer may not be well supported. It might be, I would say, might be a balance.
Yeah, I guess it's a balance between performance and flexibility, and it's a hard trade-off.
Basically what Ann said. I mean, we have definitely taken a look at Mllib before. I think the starting off point of the discussion was to make sure there's consistency, right? I think consistent between online and offline, and I think maybe it's a kind of a easy way out. I think it's just that by enforcing everything within the transformer interface, I think it's easier for us to maintain. And long term, there's also the other flexibilities that we talk about. So yes.
Great presentation, thank you. I was curious on the colors of these low-level predict methods. We've done a little bit of that, and we ended up building like wrappers, or new transformers, either delegation or extending. And that obviously implies some work whenever Spark upgrades and stuff like that. So can you elaborate a little bit on those abstractions? Is there anything you can share with us regarding that?
Yeah, I think you're probably just as familiar with the work that has to be done as we are. I mean, I'm not sure what to say about it.
I think. I think we can probably chat offline about this. I think there's a lot of things we can talk about.
I think we have a shared experience. Yeah. All right, cool. Well,
hi. Hello.
Hello.
Oh, hi.
So I had a question on, you had a model store, and what do you use to store the models, and what was your experience swapping the models on the fly for your online and offline servings?
Right. So I think we have different kind of stores. I think for a lot of the offline evaluations, I think we persist to S3, and within Uber, there's different kind of binary blob stores that we essentially upload our we compile it into some kind of jar, and then we upload it to the blob store. At online serving time, essentially, we have this access kind of management method that essentially will access and pull in the right kind of blob, download it, and then we can deserialize the jar, and then we load the models. But obviously, one of the challenges we have is how do we actually shard all these models so that we don't actually load all of them at once, and basically there was a lot of effort on there too. So.
But were you able to swap the models on the fly, or was it did you have to take a downtime for your systems to do that?
We can load a new model on the fly in online serving, if that's what you're asking, yes.
Hi, I had a question. So I have a question regarding the storage format you use to store your models. And you're following the format that Spark uses for its own models, right? Mm-hmm. So do you see any, and do you adapt the models for scikit-learn and TensorFlow into that format as well, or?
Yes, so we do, actually. We create a metadata file if you write a custom transformer that's encapsulating the scikit-learn model or the TensorFlow model, we create a metadata that looks like a transformer that Spark would use in terms of its metadata, and we create, data associated files that have the data that are needed to implement that transformer, yes.
Right, so our team actually published a blog on that as well. End of last year, it's called PyML. I think you can take a look at that.
Cool, thank you.
I'm going to take just one more question. If you do have any additional questions, you can speak to the speakers in the back. Yeah.
So my question is around the model management piece, and basically, could you comment on Michelangelo work with some model management, or Michelangelo by itself is providing model management in the sense of model versioning and model metadata and this type of requirement? Yeah.
Fully agree. I think we definitely need that, and actually that's ongoing work. I mean, it's is something that's it's still in development, that's not in production yet. So
Right, we have a model metadata that Michelangelo persists, but the versioning story is not as strong as it could be. That almost our customers are managing the versioning themselves, but we're working on that. That's an active thing we're working on. Yeah.
So there is any integration with ML flow or any those type of plan, or majorly you want to develop your own? I mean, from the current way of doing things.
We have been talking with the ML flow folks to understand, that their model and whether, we can kind of make it also fit our business and use case needs. Yep.
Great, thank you.
Yep.
Thank you, everybody, for coming. And also be sure to use the Summit app to review today's speakers. Thank you.